Hello everyone and welcome to today's lecture. So today what we're going to be covering is basic methods of counting and specifically how this relates to function properties from chapter 3. I'll summarize and describe these function properties and give examples of them as well, and kind of show what we can do with some of these basic properties. So we're going to start by defining the cardinality of a finite set. Let's start with the definition. So let S be a set if there are exactly n elements in S, where n is a natural number or non-zero or non-negative integer, we say that S is a finite set. And that n is the cardinality of set S. And how this relates to functions is we can actually think of having a function that's defined in the power sets of S, if S is a finite set, that gives us the number of elements in the set itself, number of elements in a given subset. So the notation here for finite sets typically use the number symbol, the pound sign, or a hashtag sign, and we draw the set to the right of that. So this means the number of elements in S. You could also define a function n, lowercase n, of S as well. These are both notations that are used for the cardinality of finite sets. But one of the things that we're going to see is, in general, for general sets, we can also define the idea of cardinality, so even infinite sets. So the notation in general, typically we take the double line notation to denote the cardinality of a set. So all of these are valid. Typically we reserve these two for finite sets, but in general we can talk about the cardinality of a set S using any of these notations. So just for example, a very direct example, if S is the set of elements A, B, C, then the cardinality of S can be written as number of elements in S, be written as n of S, or as the two lines right here, which look like the absolute value lines, but they're denoting the cardinality of the set. But regardless of what notation you choose to use, it's equal to 3. The book uses this notation in general, and this is the notation that we're going to try and stick to. However, we can also use these two notations as well. And we have another definition. A set S is said to be defined to be an infinite set if it is not finite. And I want to give a warning immediately right here. There are different sized or different types of infinite sets. We're going to, through the course of this lecture, define two different types of infinite sets. A countable set, which is a set that is in some sense the same size as the natural numbers, and an uncountably infinite set, which is not countable or larger in some sense than a countable set. To define this, we need a little bit more structure, but this will be made extremely precise by the end of this lecture. So kind of moving on, we'll do the first main counting result that we're going to have, and this is what's called the Inclusion-Exclusion principle. And this is formed by building up two lemmas, sometimes called the sum rule and the difference rule. The sum rule says that if C and D are disjoint finite sets, then the size of the union, the cardinality of the union of C union D, is the cardinality of C plus the cardinality of D. And lemma 2, which is sometimes called the difference rule, which says that if C and D are sets such that C is a subset of D, then the size of the set difference between D and C, or D minus C, set D minus set C, the cardinality of this is going to be the cardinality of D minus the cardinality of C. And these are both relatively straightforward to go through and prove for finite sets, using some ideas that we're going to develop a little bit later on in the lecture. So I'm going to omit the proofs of these two rules, but they're very, very, very powerful and allow us to come up with general ideas. Specifically, a theorem that I will prove for two sets is called the Inclusion-Exclusion principle. And this is if A and B are two general sets, that are finite, then the cardinality of the union of these two sets is going to be the cardinality of A plus the cardinality of B minus the cardinality of the intersection of A and B. And this is very, very important to basic counting problems and going through and really kind of figuring out how to correctly count the elements in finite sets. To give you an idea, this is not a proof, but it always helps to draw a picture here. This is saying that if you have a set A, and you have another general set B, the number of elements in A or B is the number of elements in A, which are all of these elements, plus the number of elements in B. The idea here is that if you add the number of elements in A and the number of elements in B, you're double counting all of the elements in the middle. So you have to subtract one time the number of elements in the middle to get the total number of elements. And the proof is going to be directly dependent on the previous two lemmas. And our set identities. We know that we can decompose the set A union B into three separate disjoint sets: A minus B, B minus A, and A intersected with B. So the proof of this inclusion-exclusion principle relies distinctly on this idea. We know that A union B is going to be the same thing as the set A minus B union the set A intersected with B union the set B minus A, which are all disjoint sets, are all disjoint from one another. And then by lemma 1, the size of A union B will be the size of A minus B plus the size of A intersected with B plus the size of B minus A, the cardinality of B minus A. This is our starting point. And then by lemma 2, we have that the size of A minus B is going to be the same thing as the size of A minus the size of A intersected with B. The size of B minus A is going to be the size of B minus A intersected with B, because A intersected with B is a subset always of the set B itself, and A intersected with B is always a subset of the set A itself as well. And lastly, when we take the two identities, or the two relationships from number 2 and substitute into equation 1, we're left with a cancellation. And the formula that we get in the cancellation is exactly A union B is equal to the size of A plus the size of B minus A intersected with B size, the size of A intersected with B. So this proves that inclusion-exclusion principle for two sets. It's important to note that we can also write down the inclusion-exclusion principle for any number of sets, so 3 sets or 4 sets. Specifically for 3 sets, inclusion-exclusion says that the size of A union B union C is going to be the size of A plus the size of B plus the size of C minus the size of A and B, A and C, and B and C, and then we have to add back in size of A and B and C. So you see that it becomes a little bit more complicated the more sets that you have. But we will end up proving this extension in general using the method of induction a little bit later on. So it's important for me to write this out. I'm not going to prove it right now, but we will end up proving this by the end of the course. So for 4 sets, the inclusion-exclusion principle that we get is going to be the size of this union of 4 sets will be the size of A plus the size of B plus the size of C plus the size of D minus all of the first order intersection sizes of which there are 6. Then we have to add back in all of the third order intersections, of which there are 4. And then lastly, we have to subtract out again. The final intersection of all of the sets themselves. So you can do this process and actually prove that a general formula a little bit later on. And I'll make a note of that here. So the general formula will be proven using induction later on. But this inclusion exclusion principle essentially is included with that the difference rule and the sum rule are the basic methods that we have for counting finite sets that are very, very, very useful, specifically in probability theory. We will get into that a little bit later on, into using these in various different examples. So I want to introduce some definition of some notation. If A and B are sets, and these can be general sets, infinite sets, finite sets, but in general, say if A and B are sets, you define the following notation. B with an A above it is the set of all functions from A into B. For the set of all f, such that f is a function from A to B. And this is a well-posed set because, as we mentioned today, that all functions, every function is an example of a relation. which is just a subset of the Cartesian product of A and B. And actually, it's a proper subset of the power set of the Cartesian product, because a relation is some subset of the Cartesian product between two sets, which means the set of all functions is a proper subset of the power set of the Cartesian product between two sets. And for example here, I'm going to introduce a very special function set, and this is actually the notation, the reason that whenever you see the notation 2 raised to a, where a is a set, this is the function set from a into the binary set 0, 1, using this previous notation, or the set of all functions f from a into the binary set 0, 1. And this is a very, very important set, because we'll actually see that the cardinality of this set is the same as the cardinality of the power set of a given set. And we can see this in a very simple example. This is, I'll just take the set A, B, C, and 2 to the A, the set of functions f empty set, fa, fb, fc, fab, fac, fbc, and then lastly fabc. Each of these functions can be described as follows. We know that we're going to have 8 of these functions by basic counting. Specifically for each element, right, f of a, we can have that f of a is either 0 or 1, so we have 2 possibilities. F of b, we have 2 possibilities. And f of c, we have 2 possibilities. So we know that there will be 2 times 2 times 2. This is from what's called the multiplicative rule, which we'll talk about a little bit more when we get into basic counting. But this is going to be, the size of this set should be 2 to the 3. And sure enough, when you go through and map all these possibilities out, fb is this function right here. Fa is going to be the function that takes 1 at A and 0 at B and C. Fb is going to be the function that takes 1 at B and 0 at the other 2 values. Fc is going to take 1 for a value of C and 0 for the other 2 values, and so on and so forth for each one of these functions. Fab is going to be 1 at A, 1 at B, and 0 at C. Fac is going to be 1 at A, 1 at C, and 0 at B. Fbc is going to be 1 at B, 1 at C, and 0 at A. And Fabc is going to be 1 at each value A, B, and C. you can see very clearly that this set 2 to the a, the number of elements for cardinality of the set 2 to the a is the same as the power set of A, a number of subsets of the set A. And this construction gives us a very, very general result a little bit later on. We actually say that these two sets are set theoretically isomorphic, which we will define directly in this lecture. This is a really good example of this notation and kind of showing why this notation is useful. Let's do a couple more example functions before we start getting into the properties. So we're going to define two different functions. The floor function is defined as follows. It's a function, I'll call it f, from R into the integers z. And the notation for this is that f of a real number x, put the bar with a line under it. This is defined as the largest integer that is less than or equal to x. And similarly, the ceiling function which I'll call g here in our function notation. Same thing, it maps the real numbers to the integers. This is defined by, the notation is this, and it's defined by this. Notation for the ceiling function, this means the ceiling function evaluated at real number x is defined as being the smallest integer that is greater than or equal to x. So for example, the ceiling function of pi is going to be 4. The floor function of pi is going to be 3. Where pi is the irrational number, most commonly, we'll say approximated at 3.14159. The ceiling function of the square root of 2 is going to be 2, and the floor function of the square root of 2 is going to be 1. This is a very important two functions that show up all the time, that we're going to use very heavily in our examples when we're talking about properties of functions. The next definition that we're going to have is going to be what's called the factorial function. This is a function from the natural numbers into the natural numbers that can be defined in a variety of different ways. So I'm actually going to give two separate definitions of this. But in general, if you say f of some natural number, the factorial function of some natural number, the notation you use is n with an exclamation point next to it. One definition is just define it directly as a piecewise function. This is 1 if n is 0 and the product of all integers up to and including n if n is greater than or equal to 1. Definition number 2 is what's called a recursive definition. You start by defining 0 factorial as 1, and then for any n greater than 0, n factorial is going to be n times n minus 1 factorial. And so we'll move into function properties. This is the main part of this lecture. We have two very, very special properties. The first one is said to be the injective property, which I'll define right now. A function f is said to be injective. Alternative term for this is 1-to-1. They're synonyms. If and only if f of a being equal to f of b, so if f of a is equal to f of b, then a must be equal to b. A and b have to be the same for all a and b in the domain of f. So I'll do some examples here. Let's look at f, the function from the set ABC into the set D, E, F, G. Look at a couple different examples here. So if f is a function from ABC set to D, E, F, G, this function is injective, this function is not injective. This function is injective because for all values in the range of the function, which is the range of f, or f of A, if this is the set A, the domain set is the set A, and the codomain of this function is the set B. Right, this is the set A, this is the codomain B, the range f of A of the function is the set D, E, F, and this is injective because each element of the range only has one and only one value that maps to it from the domain. This is not injective because of this E here, the range of this function right here. I'm just realizing that we're calling the function f, so having f be included in the list of terms probably isn't the best thing right here, so I'm just going to change that to h, and h. The range of this the function in example 2 is just the set D and E, but E has two separate elements from the domain that map to it, so therefore this is not an injective function. For another example, we can consider the factorial function. This is the function that we defined before, from n into itself, such that f of n is equal to n factorial. This is not injective. And the reason is that 0 factorial is equal to 1 and 1 factorial is equal to 1, right? But 0 is not the same thing as 1. Now this brings up an interesting point here, though. If we remove the the possibly bad elements in the domain or the range, so we consider a function that is slightly modified, we might get a better result. So for instance, if we consider the function g defined from a smaller domain set, instead of the natural numbers minus 0 into n, such that g of n is n factorial, defined before, where 1 factorial is 1, and for any integer greater than 1, it's defined as the product of integers, then this function is injective. Right? Because we can go through and directly show, it'd be a good exercise to prove this, that if f of n equals f of m for this function g, that m must equal n, must be equal to n. It'd be a good exercise to go through and show. But I'll just kind of draw a figure here to kind of demonstrate this. The first function f includes 0 in the domain, and 0 factorial goes to 1, 1 factorial is 1, 2 factorial is 2, 3 factorial is going to be 6. And so on and so forth. All the way down to 4 factorial, which is 24. You see that the only double mapping that we have for the factorial function is this when 0 goes to 1. So if you remove this, like I did in this example right here, and you consider just the subfunction on a subdomain, you remove one bad element from the domain of the function and consider a new function, g, without 0 in the domain. This function is in fact an injective function. So this is why it's very, very important to specify both the domain and the codomain for a given function that you're considering, because some of these properties will change drastically if you kind of change your domain or change your codomain that you're considering. This is a very, very important and subtle point that you have to always specify the sets, right? The domain set and the codomain set whenever you're talking about a given function, because very important properties will change depending on what exactly you're considering. For a final injectivity example, we'll consider the floor function and the ceiling function. And remember that we define the floor function, a function from the real numbers to the integers, such that f of x is the floor function, and g we'll call the ceiling function we defined before. Neither of these two functions is injective. And this can be demonstrated by, say, looking at the floor function of 3.5, which is equal to 3, is the same thing as the floor function of pi. And 3.5 is definitively not the same thing as pi, therefore this function is not injective. The ceiling function, you do the exact same thing. The ceiling function of the square root of 2 is equal to 2, which is the same thing as the ceiling function of 1.5. Now, an important point to make here is that if we restrict the domain, again, so I consider a new function h that maps the integers to the integers, such that h of x is equal to either the floor function or the ceiling function, this function is injective. And is really just another name for this function is the identity function. If we restrict our domain to be only integers, then there will always be, we'll always have that if h of m is equal to h of n, then m will have to be equal to n. This is another example of why it's really important to specify the domain of the function. You have to specify both the domain and the codomain of a function when you're talking about these properties. So the next big property is the property of surjectivity. Function from a to b, call it f, is called surjective. Equivalently, we can call this onto if and only if for every element of the codomain B, there exists an element A in the domain such that f of A is equal to B. An equivalent statement to this logical statement in terms of set theory is that the range set is equal to the codomain set. These two sets are equal to one another. So a function is onto if it satisfies this property. So just to show some examples, the factorial function is not surjective. Specifically, there does not exist an integer n such that n factorial is equal to 0 or n factorial is equal to 3 or so on and so forth. There are many integers that we cannot find. There exist no values such that the factorial function of that value is equal to the integer that we're considering. The floor and ceiling functions are surjective. And these are the functions that are defined from R into Z. And for any integer P in Z, there will always exist both an X and a Y in R, such that, say, the floor function of X is equal to P and the ceiling function of Y is equal to P. And using the idea developed in the previous example, in this example right here, we can see that we can always just choose the value itself, because both the floor and the ceiling functions are the identity functions. When you consider the restriction of the domain to all of R to be just the integers. And for one final example, we'll just take the function from R to R defined by f of x is equal to x squared. F defined like this is not injective because if you take, say, negative 1 and 1, negative 1 squared is equal to 1 squared, which is just positive 1. But negative 1 is certainly not the same number as 1 in the real numbers. F is also not surjective. Because there exists no real number x such that x squared is equal to negative 1. Okay, so negative 1 is in the codomain. However, there exists no real number such that the value of the function is equal to that number. However, if we restrict our codomain and our domain to be the set of all real numbers that are positive, all positive real numbers, and 0, set of all positive real numbers and 0 to the set of all positive real numbers or 0, and we keep the definition of f as f of x is equal to, and maybe I'll use a different letter to not confuse the notes with the previous example. G of x is equal to x squared. This function g is both injective and surjective. So this is a very good example showing how these properties are very, very heavily dependent on both the domain and the codomain of the defined function. And so now that we have an idea of injectivity and surjectivity, we can define our last big function property, which is the definition of a bijection or bijective. The function f from a to b is said to be a bijection or bijective this is also known as a one-to-one correspondence if and only if it is both injective and surjective. And for such functions, we can actually define the inverse function of f. Because of the fact that we have both injectivity and surjectivity. So every bijective function is invertible. I'll put a note here. Every bijective function is invertible, and the inverse of a function f is denoted by f with a -1, or in the exponent of f. And another word for a bijection, or if there exists a bijection between two sets, we say that the function is a set theoretic isomorphism. So a function I should be very specific here, a bijective function between two sets A and B is also called a set theoretic isomorphism. And this is denoted in different ways. However, a very common way is to put an equality sign with a tilde over it. And there are different types of isomorphisms, so we want to be very specific. A set theoretic is the simplest type of isomorphism. Put A, the symbol right here, with the set underneath it, and then B. This means that there exists a function g from B into A, or A into B, such that G is a bijection but this is a super important concept in mathematics, because the idea now is that if we can prove a property about one set, specifically about the cardinality of one set, and we can also then show that this set is set theoretically isomorphic to another set, the idea is that the certain basic properties are also going to extend to that new set. Very, very, very important idea in mathematics. But we'll go over some applications of this and some the really important consequences of this a little bit later on. Before we do this, I want to write down a couple more very important definitions that are going to be very, very important as we go forward. This is directly related to these bijective functions. Now we're at a time where we can actually define cardinality. The sets A and B have the same cardinality if and only if there is a one-to-one correspondence, or there is a bijection from A to B. When A and B have the same cardinality, we denote this as the cardinal number of A is equal to the cardinal number of B. And this definition applies not just to finite sets, but also to infinite sets, specifically to countable and to uncountable infinite sets, any general set. And the idea here is that for infinite sets, this definition of cardinality provides a relative measure of the sizes of two sets, rather than the measure of one particular set. We can also define what it means for two sets, one set to be of a larger cardinal number than another. if there is a one-to-one function or an injection from A to B, we say that the cardinality of A is less than or equal to the cardinality of B. The notation for this is cardinality of A is less than or equal to the cardinality of B. Moreover, when the cardinality of A is less than or equal to the cardinality of B, and A and B have different cardinality, we say that the cardinality of A is strictly less than the cardinality of B. And we denote this as cardinality of A is strictly less than the cardinality of B. And these ideas hold not just for finite sets, but also for infinite sets as well, which is really, really important. And this leads to a very, very big definition. This is the definition of countable versus uncountable. A set that is either finite, we defined before, or has the same cardinality as the natural numbers is called countable. A set that is not countable is called uncountable. And as for the notation here, when an infinite set is countable, we denote the cardinality of the set by the symbol alf naught or alf null, which is the first letter of the Hebrew alphabet. So we say that the cardinality of S is alf naught or alf null. And in the latter part of the lecture, we're going to prove that certain sets are countable, certain sets that are very important in maths are uncountable, and kind of try to explain why this is.